Okay, our next speaker is Niek Buurma. He's lecturer in physical organic chemistry at the University of Cardiff in the United Kingdom. His studies include the development of conjugated DNA binders for diagnostic and therapeutic purposes.
Thank you for the introduction, and thank you for the invitation to present our work here today. And finally, thank you to several of the previous speakers for actually introducing a lot of very important concepts in isothermal titration calorimetry. So what I'm going to assume is that everyone follows Natalia's advice and that everyone has good data, and we're going to have a look at how you can analyze that data on the assumption that your data is good in the first place. So we've seen this in the previous presentations. This is your gold standard binding curve. If you have a high enough affinity in combination with a high enough concentration of your host in the cell, your titration curve should look something like this, and you should be able to get your stoichiometry, your enthalpy of interaction, and your binding constant. So if you're lucky, this is what your data looks like. And if you are that lucky, then your ITC, the computer connected to your titration calorimeter, will contain software that can analyze this type of data. And the typical model that people use is the multiple independent binding sites model. And this gives you very rich data on interactions. We've already seen some hints about proton coupling, and I assume we're going to see more about that later on. But again, this is if you are the lucky person who has this type of data, or if you are the lucky person who can adjust their system so that you are getting this type of data by using the right conditions, the right concentrations. The problem is if you have complex equilibrium systems, and we're going to have a look at what would count as a complex equilibrium system later on. But the problem is that as soon as you have, for example, multiple equilibria that are not, that you cannot analyze in terms of a multiple independent binding site model, the problem is that you need new models, you need different models. And the question then becomes, is that model available? And for a lot of cases, the commercial software doesn't provide you with a model that you need. Is this bad? To be honest, personally, I don't think that this is bad, because what you will see with a lot of very complex models is that you have so many parameters that you can easily fit any kind of data as long as you add enough parameters. So actually, we'll see later on, if you are going to use complex models, you really need to understand what those models mean, and actually also what they don't mean. But the good news is that the ability to analyze more complex data actually allows you to really unleash the power of isothermal titration calorimetry. A lot of models are now available. We've already seen in Adrian's presentation the analysis models in terms of the binding polynomial, and I hope to show you a few more in the next few minutes. So if you have ITC data analysis, there are 5 simple steps of how you analyze the data. The first thing that you need to do is you need to calculate the concentrations of all of your components in the cell during your titration. Second thing is you have to solve your mass balance equations. You have some kind of binding model, so you have to find out what is my ligand doing, how much is there free, how much is there in this binding site, how much is aggregated, for example. You then have to calculate heat effects. You then have to find the best fit parameters that reproduce your experimental data best. And then after that, you really need to evaluate the error margins on your fitted parameters. Now, this is essentially what the commercial software that comes with your calorimeter does as well. So how does that work? Calculating cell concentrations. Essentially what you do is bookkeeping. What goes in, what comes out of the cell every time that you do an injection. So you know the amount of ligand that is present in the cell, which is the volume of the cell multiplied by the concentration of the ligand in the cell. You know how much you are adding, because that's your injection volume and the concentration of the ligand in the syringe. You also know how much you're expelling, which is your injection volume minus, the multiplied by the concentration of the ligand before you did that injection. You sum all of these terms. So this was there, this was added, this came out, this is your new total ligand concentration. And you do analogous concentrations for the the macromolecule or the host or whatever you call it. You then have to solve your mass balance equations, and your mass balance equations essentially tell you your ligand has to be somewhere. So your ligand, your total ligand concentration, has to be equal to the sum over all the concentrations of the ligands in all the different binding sites, aggregates, anywhere where the ligand can be. So essentially, all the concentrations of the ligand in all of the different modes has to equal the total ligand concentration. So the next thing that you then need is a series of equations that gives you the concentration of the ligand in binding mode, aggregation mode, X, some kind of place where the ligand can be. And you need to express that as a function of the free ligand concentration, the total, in this case, macromolecule concentration, and a series of different parameters, A, X, which describe, for example, a stoichiometry, a binding affinity, well, actually a stoichiometry and a binding affinity in this particular case. So for every place where your ligand can be it a binding site, being an aggregate, you need to come up with an equation like this. You then do a summation over all of these different terms, and that has to be your total ligand concentration. Now the problem is that for complex equilibria, you don't have analytical solutions for the equations that we're going to see in a minute. And that means that you have to solve your mass balance equation numerically. But the good news is that your mass balance is a summation over all kinds of concentrations. And because you have this summation here, it means that you can simply add or leave out terms describing different equilibria. So your system automatically becomes modular as soon as you write down your mass balance equation, however difficult it may be. So this is not a slide with a lot of equations, this is actually a picture. So just ignore that there are a lot of equations here, because apparently every equation loses you half your audience, and by this time, no, actually there are a lot of users, there's a lot of audience online, so don't switch off your computer. This is a picture, these are not equations. What this picture shows you is that you have a whole series of different equations that you can switch on and off. So here we see a system, an analysis that is completely based on the free ligand, and this free ligand has lots and lots and lots of different choices. And which choices you offer the ligand in the analysis is basically up to you in switching equilibria on and off. So what we see here, and I am happy that Adriaan mentioned something about consecutive binding models. This binding model is actually a consecutive binding model because we've defined it as if the ligand binds in the first A1 binding site, that binding event creates a second binding event, and then you have binding in a separate binding site A2. So this is actually a consecutive binding event because binding site A2 simply does not exist if A1 hasn't bound first. However, if you look at this, if you ignore this equilibrium, we have two binding sites on the macromolecule here, A1 and B1. They are in parallel, so that is the kind of situation that is not consecutive binding modes as Adriaan described earlier today. So in this case, we have multiple different binding modes, consecutive binding modes, self-aggregation of a ligand in a stepwise aggregation model, dimerisation. We have some micellization models. This is a relatively straightforward micellization model, cooperative micellization, but we've also coded a Kegel's model, which is a particular model describing micellization. The problem, of course, is, okay, so the good thing is that this is modular because we can switch equilibria on and off simply by setting the equilibrium constant to 0 or to a non-zero value. We then use a Newton-Raphson algorithm to do the numerical solution to determine the free ligand concentration in the cell, and then based on that, we back calculate all the concentrations of the different species. So once we have the concentration of the different species, we can calculate the heat effects, and the heat effects are given heat effect for every injection I for some kind of complex or aggregate X, or binding site or aggregate X, is essentially related, again, this is an incremental technique, it's related to the amount of those interactions that occur or that were formed as a result of the injection of your ligand. So again, it's a bookkeeping exercise where you know the enthalpy for a certain interaction, you know the volume of the cell, and you do the bookkeeping for how much of these interactions were present before my injection and how many are present after my injection. But you need to compensate for the fact that some of the material has disappeared out of the cell. But again, this is bookkeeping. You then do a summation over all these different contributions to the heat effect, and you add a term for the baseline, which is this one over here, and that gives you the total heat effect for every injection. So what you need now is you need to find out whether your binding model is a good model, and the way that we do that is by quantifying the fit or the goodness of fit in terms of a sum of square deviations divided by degrees of freedom. This is essentially what everyone does and what all of your software packages do, even if you may not see it. And what you now need to do is you need to minimize this sum of square deviations divided by degrees of freedom. And in our case, we use simulated annealing. And what that means is that we allow parameters to just vary randomly, and we ask essentially a Boltzmann question. If the fit becomes better, the step is always accepted. If a fit becomes worse, we will still accept with a certain random statistical chance that this step is going to be accepted. So not all the steps in our optimization method always lead to a better fit. We allow the fit to become worse from time to time, but that happens with a certain Boltzmann factor. What we then do is we have a kind of virtual temperature which decreases, so steps going up become increasingly unlikely until at the end we freeze everything and we have the best possible fit. The evaluation of error margins is then the last thing that we need to do, and for that we analyze the trajectories of our simulated annealing process. And as an example, this is the parameter validation for the standard titration that you will do to test your instrument, your calcium and EDTA titration. What we do is we plot a normalized sum of square deviations divided by degrees of freedom as a function of a parameter value. And what you should get for normally distributed errors is something that looks like a parabola like this, and everything that is below, that is in between the normalized value of 1 and 2, all those parameter values should be or are considered to be within the error margins. So in this case, you see that we have a binding constant of 2.4 times 10 to the power 6, I think it was, but 2.2 is still within error margins, 2.6 is also still within error margins, because it is just below the cutoff of 2. So we make plots like this, and also three-dimensional plots, to analyze what the errors look like. And the advantage of this is that if your error is not standard, you will be able to see that as well. So as an example where we make a three-dimensional plot, what you see here is the sum of square deviations, in this case not normalized, divided by the degrees of freedom as a function of two parameter values. And what we see here is that we have a massive blue region at the bottom of this valley. And what that means is that there is very strong parameter correlation between the equilibrium constant and the enthalpy of interaction. So all of these values here all correspond to good fits. And we can visualize in this very convenient manner how strongly these parameters correlate. So in this case, we also knew that we actually needed to get better data, because this, of course, is not going anywhere. So just very briefly, this is the software that we've written to do this. It involves a data preparation package, a fit package, and then post-fitting parameter validation. And it allows you to do numerical analysis for modular sets of mass balance equations. So what this means is that any kind of forest of interactions, as you see here, we should now be able to tame. And what we're going to do is we're going to have a look at 6 very brief case studies. And I'm leaving one case study out, which is the cooperative self-aggregation of surfactants, because I suspect that the next speaker is going to address that particular problem. So we'll look at 4 examples involving coupled equilibria for nucleic acid binders, and we'll look at 2 examples involving nanoparticles as well. So the first problem, and this is actually why we started to develop the software, had to do with ligand self-aggregation. This is a very famous DNA binder. It binds in a minor groove. It's the best known a DNA binder. If ever you need a technique, or if you want to develop a technique that identifies whether something is a groove binder or an intercalator, you'll use this molecule as your test molecule because everyone knows it's a groove binder. The problem with carrying out ITC experiments with this compound is that if you look at the heat effect of dilution, this is non-constant. And what that tells you is that this particular molecule is aggregating. Every time that you do an injection, the aggregates fall apart, but every time you do an injection, the concentration of your ligand in the cell goes up as well, and that means that the second injection, a consecutive injection, the amount or the fraction of the ligand aggregates that are falling apart decreases. And as a result, you get non-constant heat effects of dilution. The problem with this type of data is that you get identical fits for two different models. So there is a stepwise aggregation model, and if your stepwise aggregation model says your equilibrium constant is A and your entropy of interaction is B, then a dimerisation model gives exactly the same fit. The only difference is that it will tell you that your equilibrium constant is half of A and your delta H of dimerisation is 2 times B. But this actually gives you a way out, because we've seen the Van Hoff equation before. We have a factor of 2 difference between these 2 equilibrium constants. And the good thing about that is, as soon as we start taking logarithms, that turns into a simple 0.3 of a step on a logarithmic plot. So that's what we've done here. We've plotted the data as a function of temperature. We've done these experiments at different temperatures. These are the equilibrium constants of self-aggregation if we analyze the data in terms of a stepwise aggregation model or in terms of a dimerisation model. So you can see that the data points are on parallel lines, but the slope of that line should be your entropy of interaction. If we now plot the entropy of interaction centered on the first data point, and actually in this case we use the Clark-Glue equation, so we include delta Cp as well, we get a blue line that follows the data points. Whereas if we look at the red data, similarly the thermodynamic or the calorimetric entropy plotted through the data points doesn't reproduce the data points. And that means that in this case, this ligand aggregates in a stepwise manner. Now this came up earlier already. We did this in different buffers to make sure that there is no entropy of protonation of the buffer that goes into these experiments. So you do have to know what you're checking. We check this using diffusion NMR in this case, and the red line is a dimerisation model, the blue line is a stepwise aggregation model, and although neither line actually reproduces the data phenomenally well, the blue line is clearly a lot better than the red line. So again, this is stepwise aggregation. If we then look at the titration of this compound, if we titrate DNA with this compound, what we get is a long titration where we have a first binding mode, a second binding mode, which is actually relatively boring. It's boring because if you use the concentration that you use in the syringe here for this part of the titration as well, you wait for a very long time. And then at the end, we saturate the second binding site and we see the dilution at the end of this. Now the reason that ITC was the technique to use here is because the second binding mode is invisible in spectroscopy. And that means that you can only see this if you use ITC. The other thing is there is a jump in the data here, and that is because we allowed for using different concentrations of the ligand in the syringe, so that you can focus on different parts of the titration using different injection concentrations of the ligand injected. A second case, this is very briefly, sometimes aggregation of your compound is not bad at all. For this particular compound, and this is in collaboration with people at Strathclyde University, for this particular compound, dimerisation of the compound, the dimers then aggregate, but the dimers happen to be in the right shape, the right relative conformation that resembles the dimerisation in a minor groove as well. So in this case, dimerisation is actually helping the binding rather than stopping the binding. Okay, so another example of comparing spectroscopy with calorimetry. This is a compound that we've been interested in carrying out DNA binding studies with. And what happens with this particular compound is if you titrate it with DNA, so you start with a solution of this compound, you add more and more DNA, you see a very steep decrease in the absorbance at the beginning, And after that, you get something that looks like a normal binding curve. And the question then becomes, what can you do with the data that you get here? And that is a question because what people normally assume, if you're dealing with a well-behaved binder, is that you start your titration, all your ligand is there, you add a little bit of DNA, your binder binds to the DNA as it is available, and the rest of the ligand molecules are completely well-behaved and they wait for more DNA to be added. But this is not what happens in practice. In practice, binders often behave badly because they're, especially DNA binders, they're cationically charged. Because they're cationically charged, which means that these binders are not going to wait for more DNA to be added. They're going to coat the DNA on the outside and everything is going to precipitate, which may be very difficult to see if you're working at very low micromolar concentrations. The consequence of that for your binding models is that if I now add a second bit of DNA, this is the situation that I had. I had this DNA with all the ligand bound to it. I add 2 more strands. These 2 new strands are not picking up my ligand free from solution. They're actually picking them up from the secondary binding sites on the first bit of DNA. And that means that my equilibrium constant is not picking up the ligand from solution. It is more like an apparent equilibrium constant for competition between different binding sites. So the question then becomes, does this actually mean anything? And we've done simulation based on data that we got from calorimetry data, which suggests that in a lot of cases, it really doesn't mean anything near what you think it might mean. It looks as if you probably get a lower limit for your affinity constant, but it can be several orders of magnitude off. So for this compound, the advantage, if you then look, if you use ITC, the good thing is that your DNA is present in the cell at a relatively high concentration, and after your first few injections, this is the scenario that you're in. You have a few bits of DNA, but with even less binders. So this is what we wanted to do, and this is what we did. So this is the ITC data, raw data at the top, and the integrated data at the bottom. We analyzed that using our software, and this is our fit. So what do we see? First of all, we can fit the data reasonably well, apart from the fact, of course, that this is by definition going to become a plateau in our software because we assume that this is simply a secondary binding site. It looks as if the data has a bit more pattern here than we actually, wanted to have. No, we can't demand nature to behave the way that we want it to behave. There is more pattern there, so it means that this binding model, even though it does a reasonable job at approximating the data, there is something else going on which may need a more complex binding model. But what we see is we can now actually really get a good feeling of what the different binding modes are. We can get the stoichiometries, whereas from the UV visible titration that would have been impossible. So again, this shows the power of ITC. A fourth compound, this, again a collaborative project, this is a hybrid DNA RNA binder. So this particular compound, again, DNA binding data and dilution data was available. Again, we see a non-constant heat of dilution over here, which means that this compound is self-aggregating. We also see very, very, very reproducibly that this heat of dilution is non-constant. Whatever concentration ratios we use, it's not constant. And that means that there have to be at least 2 binding sites here. So we analyzed this data in terms of a binding model that had self-aggregation and 2 binding modes, and we get this fit to the data. Now, what does that model actually mean? And the key bit of information is, again, looking at the parameter correlation. If we look at if we look at the 2 stoichiometries for that first binding mode, let's go back. So we have 2 different binding modes in this region here. If we plot the goodness or actually badness of fit as a function of those 2 parameter values, what we get is perfect correlation, this whole blue valley here, where any of the combinations of these 2 stoichiometries gives a good fit. And what that means is that we cannot identify the 2 different stoichiometries. We can only really quantify the sum over those stoichiometries. And this type of plot immediately shows to us that it is impossible to identify them individually. We did then have a look at lots and lots more of these plots, and we were able to then identify what the most likely maybe even the least unlikely binding mode for this compound was. So the self-aggregation made the system a little bit harder, but numerical analysis allowed us a way out. Very briefly, you can also use ITC for, well, in combination with nanoparticles. This is a series of titrations involving cationic magnetic nanoparticles interacting with DNA. So again, the fact that those nanoparticles may scatter light really doesn't stop you from doing the experiment. And what we could show in these titrations, for example, is that there is a continuous interaction going on right until the moment where everything precipitates. So this precipitation was not a cooperative event, it was the result of multiple interactions. Alternatively, if you want to count the number of thiols, for example, on a gold nanoparticle, you can titrate thiols like this straight into naked nanoparticles. Again, analyzing the data, you can count the number of thiol molecules on the nanoparticle, and in that way you can determine the surface coverage of your nanoparticle with thiols. So, in conclusion, ITC provides valuable and unique data on coupled equilibria. And you can analyze these coupled or these complex equilibria, and as we've seen, and we're going to see more probably later on, there are a lot of different models available in the field that you could use. The possibilities are endless, but the key thing is to make sure that you really look at the validation of your optimized parameters, that they are meaningful, because it is very easy to keep switching on equilibria and get a perfect fit that is absolutely perfectly meaningless. So acknowledgements, I've acknowledged the collaborators who have provided compounds and interesting challenges, some at Cardiff, several involving DNA binders, people looking at diffusion NMR and small angle neutron scattering, which was important for the surfactant data. People, mainly from BIGO actually, looking at nanoparticles, and several people again from BIGO and from Cardiff looking at surfactant solutions, which I didn't discuss. My group for actually doing the titrations, if they're watching, they know which titrations they've done. The funders are a wonderful combination of EPSRC, Cardiff University, the EPSRC Directed Assembly Network, the BioE Initiative, and both the Saudi and the Kurdish governments. And with that, finish, and thank you for your attention.
Okay, we have time for questions.
This is a question, I think is again from Stefan Geschwinder from AstraZeneca. He asks, how often can you relate energetics ITC data with structural biology? In the sense of, can you relate a delta H value with a structure where you see a hydrogen bond being acquired?
Would I ever want to decide that something makes a hydrogen bond based on ITC data alone? The answer to that is probably no. However, if I had a series of structurally similar compounds binding to the same target, and I could introduce or take out that hydrogen bond, I would probably start to begin to consider interpreting that data in terms of whether the hydrogen bond is there or not. The next question then always becomes, do you want to relate this to, for example, computational data? So if you know a computational chemist, they may actually be very happy with the enthalpies that we can provide. So there are models of interpreting enthalpies in terms of buried hydrophobic surface area. And in that sense, you can, to some extent, count hydrogen bonds. But if there is a critical question, can you identify whether one hydrogen bond is formed or not, then I wouldn't want to use ITC all by itself. Then again, I probably would not want to use any technique all by itself, apart from maybe something that gives you 95% certain information on the structure. So I guess NMR data, crystallography data. But maybe I'm too scared.
Yeah, another question?
I have a technical question regarding the very beginning of your presentation when you showed the sum of square function that has to be minimized. And essentially, when things go well, we call that a chi-square. But for having a chi-square, that means what you have divided the sum of square by the degrees of freedom. But so, did you try to divide by the estimate of the error on each point? That means, do you try to get error estimate on the experimental data so that you transform your sum of square divided by the degrees of freedom to a real chi-square, which can be used in more statistical evaluation? Because we know the chi-square distribution.
That's an absolutely perfect question. We both cheat and we check anyway. So ideally, there is the problem with my heritage. I will pronounce this name, and if this person is watching, they'll laugh at my pronunciation of their name. There is someone, Tellinghausen, in the United States, who has estimates of what the errors on the different heat effects would be. Technically, I think the best thing that we could do is use those estimates of what the different errors would be and include those to calculate a real chi-square. That's absolutely right. We haven't done that. And in that sense, well, no, not in that sense. You're absolutely right. What you would expect based on a chi-square test is that your optimized function would be at 1. So, and that is where this idea comes from. Everything between 1 and 2 is within error margin, because that corresponds to a delta chi squared of 1, which indicates your error margins according to statistics. So we've normalized this. The reason that we've normalized this is, so in a way we cannot check whether our model is a good model. However, in the output of our software, one of the things that we get is the average deviation per data point throughout the titration. So what we do instead is we check whether the number that comes out, the error per injection, whether that is a reasonable number compared to what we know from the instrument. So we don't do the check at the point where we should do it, because we haven't coded in what I would call Tellinghausen errors. But instead, we check that the average square deviation, the root of the average square deviation of the data points compared to the fit is lower than 1 microcalorie, unless the heat effects are massive, and then we allow them to be a little bit bigger. Sorry, I need to add to this that we have a WIDEN-ITC. So this is why the errors on the heat effects are basically they're errors of larger numbers. So percentage-wise, they're not big, but that's how we check, rather than the formal check.
This is another question of Geoff Holtgate from AstraZeneca. He comments, we have seen several different analysis approaches already today. Should academics and instruments providers working more closely together to provide better solutions for complex data analysis? For example, the complex models you describe as well as WIDEN-ITC and NITPIC.
Well, true, and exactly, we're going to see even more models. Should they? Yes, absolutely. And if I want to translate this question, we must, and the only way of making sure that we can is by making sure that there is funding for this type of work, which is maybe a horrible way of turning this into a funding-related question. But yes, it's absolutely true. However, there needs to remain a certain amount of diversity. I think one of the good things is that different people collaborate by comparing their solutions against each other. Otherwise, depending on the size of the community who are developing these data analysis methods, we run the risk of all agreeing on the wrong thing. So the advantage of having multiple solutions is in close collaboration, making sure that what we analyze is actually meaningful, not just in one data analysis method, but also in another slightly different data analysis method, using the same principles, but implemented in a different way. And the only way we're going to be able to do that is, yes, collaborate between the different people who develop the models, collaborate with the instrument providers, so that we know exactly, to the minute detail, what we can expect and what we can't expect from the quality of the data.
I think this is the last question from Neela from Pennsylvania State University. She's asking, or is uniform size distribution of a nanoparticle crucial for a good ITC data?
No, it's not for good ITC data, but it does become important for the interpretation of the data. So in this case, the nanoparticles were provided by a group in Vigo who have a lot of experience in making very monodisperse nanoparticles. So because of that, we can count the number of thiols that went onto the nanoparticles, and in the magnetic nanoparticles, we got good stoichiometries, and we can then relate that to the size of the nanoparticles. If you So the bottleneck in this case is not the quality of the data that you're going to get. The bottleneck is actually how you are going to interpret that data. If you know that you have a very polydisperse mixture, you probably need to get some kind of an idea of where it becomes difficult is that your surface area is going to change relative to the total amount of gold that you have in solution. And because you're looking at surface area, you're going to get a really wide distribution. You can still calculate the average number of thiols on an average nanoparticle, but the interpretation becomes trickier. But apart from that, the data is perfectly fine.
Okay, let's thank Niek for his presentation, please.